Hey, what's up SM3? In this video, we're talking about transformations of exponential and logarithmic functions. So, in the last couple days, we've talked about exponential and logarithmic functions. Now it's just time to graph them with the transformations. So, transformations, I hope that you guys understand and recognize that transformations don't change from function to function. The functions change, but the transformations and how you apply them do not. So, for example, um, let's take for example the absolute value function. The absolute value function, which was absolute value of, let's say, x minus 3. Now, this function right here is an absolute value function, which just looks v-shaped, right? And this transformation, because it's subtract 3 inside, it's a horizontal translation, which means you move right 3. If it was the absolute value of x plus 2, then this would be left 2. Okay? Now, that doesn't really change. As you notice, as we went to radical functions, so if we had x plus 3 here, this would be a square root function that went like that. But if it was plus 3, then it would just be left 3. Right? So if it was plus, you went left. If it was subtraction, you went to the right. It was also the same for parabolas and polynomial functions. So if we had x plus 2 squared, this was left 2. And this was a u-shaped function, like that. So it's really not different for exponential and logarithmic functions. The only difference is the type of function that it is. So for exponential functions, it's all about what you define as the inside of the parentheses. So for example, in these examples right here, the inside is the exponent. So if I have 4 raised to the x minus 3, this right here is the inside of your parentheses, the exponent. So if I have minus 3 inside the exponent, then this is going to be right 3. And if it's 4 raised to the x plus 2, this is just an exponential. It's just going to be left 2. Exponential functions just look like this right here. So you could have exponential growth or exponential decay, like that. Okay? Now, if it's not inside the parentheses, if there's nothing being added or subtracted inside the parentheses, that means it's going to be outside like this. So this plus 5 and this minus 1 means that it's outside the parentheses, and this is where we have a vertical translation. So you can see how similar transformations are. They apply the same way, it's just the function that's different. So if we come down here to example 1, well, I guess before we get into that, we need to make sure that we understand what an exponential function is. So an exponential function takes on the form, so the parent function of an exponential function is y is equal to b to the x power. Transformations look like y is equal to a times b to the x power. You can do plus or minus h and then plus or minus k, I guess you could say. But if we just want to save time, we can just say x minus h plus k. So these are the transformations that we're going to be talking about today. But this is the parent function. Now, b doesn't really have anything to do with the transformations. B is just the base number, so don't get confused by that. So in this example, we have 1/2 raised to the x power. Okay? Now, 1/2 doesn't mean that it's a vertical stretch, or doesn't mean that it's a horizontal stretch, or anything like that. That's just the base. Okay? That's just the base of the function, of the exponential function. Now, if b is greater than 0, this is going to be exponential growth. If b is less than 0, then you're going to have exponential decay. And the difference is that growth goes up like this, while decay goes down in the opposite way. Okay, so make sure you understand that. But it might get confusing when we talk about horizontal reflections. So reflection right here, a reflection in the y-axis. So for this example, if we were to take 4 to the x, that will just look like this right here. This is something like 4 to the x power. But so this is exponential growth because 4 is sorry, did I say greater than 0? I think it should be 1. We should be writing 1, not 0. So b is greater than 1, b is less than 1. So this obviously is greater than 1, so this is a function greater than 0. Or greater than 1, so it's exponential growth. However, 4 to the negative x, because it's negative being multiplied inside, this is a reflection in the y-axis. So that means it's a horizontal reflection, so that means it changes to go like this. So even though 4 is greater than 1, you're reflecting it over the y-axis, which makes it an exponential decay function. So make sure that you understand that, and we'll get some practice in that as well. Alright, so let's just get to doing some examples. Before, one more thing. Exponential functions have what's called an asymptote. So make sure we know what that is. So an asymptote, which is spelled like ASYMPTOTE. So it's a line that the function approaches but never touches. Okay. So in this example right here, we have y is equal to 1/2 to the x. So I'm going to show what this function would look like. Now, 1/2 to the x. So b is less than 1. So this is going to be a decay function. So it's decay, meaning it's starting high and coming low. Okay. Now, there are no vertical transformations or horizontal transformations happening with this function. This is a parent function right here. So when x is 0, this is going to be 1/2 to the 0, and anything to the 0 power is 1. So that means when x is 0, y is 1. And again, we know that this is a this is exponential decay. So I'm not really sure about the specifics of where it's going to go right now, but I do know it's going to go like this. Now, we've talked about it before. This line will get closer and closer to that x-axis, but never actually touch. This line right here is called this is what the asymptote is. This is the asymptote line. It's the line that the function gets closer to, but never actually touches. Okay? So the asymptote will move with any sort of translation. So horizontal, or any sort of, I guess, vertical translation. It won't move with a horizontal translation, but with a vertical translation. So first of all, let's describe the transformation from f to g. So from f to g, we have f of x is equal to 1/2. F of x is equal to 1/2 to the x power, and then g of x is equal to 1/2 to the x power minus 4. So if we look at this table up here, we have a function in this notation subtracting 4, which means we go down 4 units. So it's a vertical translation or a shift down 4 units. Okay, and I'm going to erase this right here. So if we're going to be down 4 units, that means the asymptote is going to move down 4 units. So the asymptote was originally at y is equal to 0. So I'm going to draw 1, 2, 3, 4, 5. So I'm going to draw my asymptote right here. Sorry, I'm going to draw my x-axis right here and my y-axis right here. So my y and my x. Now originally, my asymptote ran right through the x-axis. But since our function is shifting down 4, I'm going 1, 2, 3, 4. I'm going to shift my asymptote down 4 units. So right here, that's my asymptote line. Okay, so this is the line that the function gets closer to but doesn't actually touch. Now again, as I drew out before, the parent function touched right there, which means that this point right here is also going to move down 4 units. So it's going to be right here. Okay? And that's going to be our graph. Now, we could also make a table so that we know where to the left and to the right that this function is. So we can make an x and a y table. So let's say what happens when x is going to be, let's say -2. Or let's do -1. So when x is -1. So if we plug that into a calculator, so we're going to plug -1 into there. So let's try that here. So if I have 1 divided by 2 raised to the -1 power, I get x is equal to 2. But also remember that there's a vertical shift. That's going to be -4. So then -2. I'm plugging it into this one right here. So when x is -1, our function's at -2. So let's say when x is equal to -2. So if we do 1 divided by 2 raised to the -2 and then subtract 4, so we're at 0. So that's right here. Okay, now you can keep going. I think we kind of have a good idea about the general shape of it though. Okay, it's going to look something like that. Okay, let's move on to another example. So, translating a natural base exponential function. So, describe the transformation of f of x equals e to the x, represented by g of x is equal to e to the x plus 3 plus 2. Now, so this is a natural base function, right? Because the base here is e, so we call it the natural base function. And we talked a little bit about this before. We graphed it a little bit. So let's talk about the transformations here. So inside we have plus 3. And so if we look at our table, if it's inside and you're adding, so like right here, if it's plus, that means you're moving to the left. So from f to g, the transformations are shift. So I guess I should say horizontal shift. That's going to be left 3 units. Okay, and then plus 2. This is not inside the parentheses, it is outside. So that's a vertical shift. So vertical shift, and this one's just going to be up 2 units. So left 3 and up 2 units. Okay, now, so if we're going to do that, we have to move the, now the asymptote doesn't move with the horizontal shift, it will move with the vertical shift. So if it's going to be up 2, so if we had like our y-axis right here and our x-axis right here, this is where the asymptote lies. but the function, so this exponential function, is going to be moving, it's going to be moving left 3 and up 2, so that means this line is going to move up 2. So it's going to be right there at x is equal to 2. So y is equal to 2, sorry. So I'm still going to keep my x-axis right there, and my y-axis I'll go ahead and keep right there as well. Now I know that my asymptote is moving up 2 units because my function is moving up 2 units, so there's my asymptote. So my natural base function will look like this from here, but also it's moving to the left 3. So again, if we were to create our point, now here if we put x equals 0, here we get e to the 0, and that's equal to 1. So the function will hit right here. This function here will hit right here, but we're moving it to the left 2 units. So this means we're going to move it, we're going to move it left 3 units. So 1, 2, 3, so our function will be right there instead. Okay. Now if you wanted, you could plug in some points, which would be fine, but I'm just going to go ahead and just draw what I think it might look like. It's exponential, but it's going to look something in that sort of way. But yeah. Okay. So again, you notice how the function shifts. So this point right here, the parent function would have normally hit right here, but the transformation says we're going to shift left 3, so 1, 2, 3, and then up 2, 1, 2. So you see how we landed in the same spot. Okay. Now let's go to example 3, transforming exponential functions again, but this time with a little bit different. This time I think we're talking more about reflections and stretches and shrinks. So describe the transformation of f to g and then graph. So for a, we have f of x is equal to 3 to the x. Remember that this right here does not represent any sort of stretches, horizontal or vertical stretches. This is simply the base. If it's going to have any sort of horizontal or vertical stretch or shrink, that means it has to have an a times b to the x, so that means this number has to be multiplied by another number, or x has to be multiplied by another number. So in this case right here, x is being multiplied by 3. Okay? X is being multiplied by 3. So if we look up here, if x is being multiplied by 3, so that's this right here, that's inside. So it is inside, that's being multiplied by 3. Okay? So if it's inside and it's greater than 1, this means it's a horizontal shrink by a factor of the reciprocal. Again, this is stuff that we've already talked about with other functions. If it's being multiplied inside, you always read it as the reciprocal. So if it's greater than 1, it's a shrink by a factor of that. So if we come back down here, so describing the transformations here, you have from f to g, you have a horizontal shrink by 1/3. Horizontal shrink by 1/3. Now, if we had something, this is just for example, so you don't have to write this down, but if we had g of x is equal to 2 times 3 to the x. Okay, again, this number right here has nothing to do with whether or not it's a stretch or a shrink, horizontal or vertical. It's just simply the base. So I know it can get really confusing, because it's another number and it looks like it's being multiplied. But so try not to get that confused. This number right here is where we'd get into a vertical stretch or a vertical shrink. Okay. Okay. So we know that the horizontal shrink by a factor of 1/3. Now the other one here, so we have subtract by 5. So again, that's going to be a horizontal translation. This is just like the ones that we talked about before. So horizontal shift, and because it's minus, you're going to go right 5 units. Okay. So these are the two transformations that we see for the function f of x is equal to 3 to the x power. So there's no vertical transformation. So nothing vertically is happening to the function. So we're not going to move the asymptote. The asymptote is going to stay right here. So the asymptote is going to stay at the x-axis. Okay. Now the parent function, again, if you plug 0 into the parent function, you're going to get 1. So it's going to cross right here. Okay. But in any case, I'm just going to make a table of what's going on. So if I make my table, I'm going to make that over here to the right. So let's plug 0 into the function. I'm going to plug it into the g of x function, and let's see what we get. So that's going to be 3 to the negative 5. That's going to be something really, really, really small. Okay, so I'm not even sure if it's worth putting that. So it's going to be somewhere like super down right here. Now remember, we're shifting to the right, but then we're also shrinking it by a factor of 5. So let's see what happens if we were to plug in something like x is equal to 2. So if we plug 2 into the function, here that means we get 3 to the 6 minus 5. 6 minus 5 is equal to 1, so 3 to the 1 power is just going to be 3. So when x is 2, y is 3. Okay? And honestly, that should be pretty good enough for us to graph. I just want something, those 2 points would be good, because we know the asymptote's going to go through there and up, then it's going to keep going up like that. Now, the reason why it doesn't look like we shifted over 5 units, because remember how we said that we would shift over 5 units. Now, the reason why it doesn't look like that is because we're not just shifting it over 5 units, but we are also compressing it horizontally by a factor of 1/3. So that means the values are compressing by 1/3. So yes, we did say that we'd be shifting over to the right 5 units, which would be somewhere over here, but that the shrink makes the values of x come in by a factor of 1/3. Okay, so that's why it's a lot easier to just start plugging in numbers and try and find a nice number that will work. Okay. Now for b, so this is a exponential function, but it's a natural base function because the base here is e. So the function here is e to the negative x. So because it's negative x, this is an this natural base function is actually decay. So it's going like that. So it's a decay function. Now from f to g, we're multiplying it by negative 1/8. So this is an outside operation. We're multiplying outside. So if we're multiplying outside, this is going to be a vertical stretch or a shrink. And right here, it's by 1/4, which means it's going to be a shrink by 1/4, but in our case, it's 1/8. So this is going to be so the transformations from f to g are a vertical shrink by 1 over 8. Vertical shrink by 1 over 8. Now, there's one more transformation, that's the negative. So if we multiply by negative, now this time it's outside, not inside, which means it's going to be right here. It's a reflection in the x-axis. So this is a vertical, so a reflection in the x-axis. Okay. So here, instead of it going like this, if we're going to flip it over the x-axis, our function is actually going to look like that. Okay? So vertical shrink by 1 over 8, a reflection in the x-axis. There's not going to be any shift, horizontal or vertical. Okay? So what that means, I'm going to draw my x-axis up here and my y-axis right here, because I know I went from going like this, now I'm going to be going like that. Okay, now if I create a x and a y table, now if I plug 0 in for x, I get negative 1 over 8 e to the negative 0. This is just 0, and anything to the 0 power is 1. So this is going to be negative 1 over 8 times by 1, which is negative 1 over 8, and that's going to be a really small value. So something like that. So negative 1 over 8. So if we plug in, let's try just plugging in, let's say something like, so I know it's going to go this way. Let's plug something like negative 1 into the function. Now e is going to make things a little bit difficult because e is a irrational number. So let's just go ahead and plug that into a calculator. So if I have negative 1 divided by 8 second e raised to the positive 1, because I'm plugging negative 1 into negative x. So then I get 0.339. So that's going to be, again, still really small value. So if I plug in something like negative 2, so it's going to be e squared. And then if I multiply that by negative 1 divided by 8, I get pretty close to 1. Okay, so we're making some progress. In any case, I know the general shape of this, and it's going to keep getting bigger exponentially, and it's going to make a shape like that. Okay, so that should pretty much do it for the exponential functions. Now I'm going to split this up into two different parts, where next video we're going to talk about the logarithmic functions, and so we'll cover that in class on Thursday actually. So we're splitting this up into 2 different days. So yeah, stay tuned for the next part where we cover logarithmic functions.